Lesson 2-1 is on relations and functions. If you recall from Algebra 1, a relation is just a set of ordered pairs. But in a function is a relation in which each element of the domain, that is the x's, is paired with exactly one element of the range, that is the y's. In other words, each x goes to only one y. In a function, there are no repeated x's. Your textbook goes on to talk about different types of functions, one-to-one, onto, and both one-to-one and onto. I think we're just going to, you can read that, be aware of it. We're not really going to focus on that in this course. And I think I'm going to skip example 1 also. Let's go on to talk about discrete and continuous relations. A discrete relation is graphed as a set of dots or unconnected points. And you can look at this example down here. It's just a bunch of dots. And I remember that because both discrete and dots begin with D. A continuous relation is graphed as a line or a smooth, uninterrupted curve. So it's kind of like this second graph here. Okay? Continuous curve, that's how I remember that. But also remember that a line, a straight line, can also be considered a continuous relation. And here's an important point. The domain must have an infinite number of elements. In other words, you must be able to have x be any real number, or all real numbers. The vertical line test, you probably remember this from Algebra 1 as well. It's a way to determine if the graph of a relation is a function. The way you do that is you take a vertical line and you run it across the graph of the relation, and if it only intersects the graph at one place at a time, then it is indeed a function. So we're going to graph each equation here and then determine whether it's one. Actually, we're not going to do that. We're going to graph each equation, determine the domain and range. I think we're going to skip the, oh wait, we do want to determine if it's a function, but we're going to skip the one-to-one, onto, and both, and then state whether it's discrete or continuous. So our first one is y equals 5x plus 4, and it's possible to do this on your calculator. If you forget how to do that, come see me. But in the meantime, I think I'm just going to use the old traditional form of y equals mx plus b. My b is 4, that's my y-intercept. My slope is 5, which means up 5 and right 1, or down 5 and left 1. And there's my graph. Oops, it's a little crooked there. But this is indeed a function. Oh, let's do domain and range first. So my domain, it's actually, since this is a straight line, my domain is all real numbers. Because x can be any value. And my range is also all real numbers, because y can be anything as well. And here's just a little bit of a hint. This here is going to be true for every non-vertical line. So for every line except for a vertical line, and we'll talk about that in just a minute, this will be true. The domain and range are going to be all real numbers. And this is indeed a function because it does pass the vertical line test. As I move a vertical line across the graph of the function, the pink line only crosses my vertical line in one place at a time, and it is a continuous function. There are no breaks, there are no dots. Okay, let's try graphing y equals 3x squared. Let's see, so I'm going to go ahead and make a table of values for this one. And I'm going to use -2, -1, 0, 1, and 2. And remember, you can do this on your calculator. Come and see me if you forget how to do that. So when I plug each of these numbers in, I get these values here. And your calculator will also make a table for you, which is kind of a nice little bonus there. -1, 3, 0. Okay, and mine kind of goes off a little bit here. Graph as best you can. Okay. For this graph, my domain, again, is the set of all real numbers, because x can be anything. And the range, well, the range is a little more complicated here, because remember, the range is the y's. So notice in my table, I don't have any negative numbers. In fact, my smallest number is 0. So it is not possible to have any of your y's be negative numbers. Because notice, if I plug in, no matter what x I plug in, I square it, that makes it positive. So my range is the set of all y's such that y is greater than or equal to 0. This is indeed a function because it passes the vertical line test, and it is also continuous. My next graph, this one's a little tricky, and you cannot do this one on your calculator because your calculator requires that the equation be written in y equals mx plus b form, or y equals form. This is x equals 5. This is a line you should just memorize. This means that no matter what y is, x is always 5. So when y is -2, x is 5, and so on. And in fact, the graph of this is a vertical line through 5 on the x-axis. Anytime you have a vertical line, its equation is x equals a number. And conversely, whenever you have an equation x equals a number, it's going to be a vertical line. The domain of this, so what can my x's be? X can only be 5. The set of all x, such that x is equal to 5. And in this case, my range can be all real numbers. Okay, this is not a function because it does not pass the vertical line test. In fact, when you move your vertical line over x equals 5, my vertical line intersects the graph in an infinite number of points. And even though there are no breaks in this, this is not a continuous function. It's not continuous because, remember, the domain has to contain all real numbers, and it does not. The domain only contains 5, the number 5. A couple terms you may remember from Algebra 1. The independent variable, that's generally the x. Those are the values that you choose to put into a function. And in science, the independent variable is often the time, and that's going to be on the horizontal axis. The dependent variable is generally the y, and you can think of it this way. Its value depends on what the value of x is. Function notation is f with an x in parentheses, and we say that f of x. It is not f times x, it is not fx. F is not a variable. It's just a fancy way of saying y. And it's actually kind of a nice way to talk about a function because it shows the independent variable x as a function of the dependent variable. In other words, the x is in f of x. So let's look at a couple examples here of using function notation. Given that f of x is equal to -x squared plus 3, find each value. What this means, if I have to find f of 5, is I'm going to plug 5 into my original function wherever I see an x. So instead of -x squared, I'm going to have a -5 squared plus 3. And now we just PEMDAS that. So -25 plus 3. Remember, you want to square it first and then make it negative for a final answer of -22. So what that means is that when x is 5, f of x is equal to -22. Let's try another one here. F of -3. So I have negative, that negative stays out front there, but then my x is a -3 squared plus 3. Don't think that these negatives just cancel each other out and make a positive. It's going to be -3 squared, then take the opposite of that, and then add 3. So that's going to give me a -9, because -3 squared is 9, and there's my negative, plus 3 gives me a final answer of -6. So f of -3 is equal to 6. And let's try one here that has some fractions in it. if g of x is 2x squared minus 4x plus 1, that should be a g, find g of 1/3. So I'm going to take g of x and plug in 1/3 wherever I see an x. So 2 times 1/3 squared minus 4 times 1/3 plus 1. I want to square first. 1/3 squared, 1/3 times 1/3 is 1/9. 4 times 1/3 is 4/3. And that's going to give me 2/9 minus 4/3 plus 1. Go ahead and use your calculator. Remember to put parentheses around the fractions, and that gives you a negative 1/9. So g of 1/3 is a negative 1/9.